Okay, just one slide. Maybe some of you have seen this already from my previous classes, but anyway. This is a brief history of dense linear algebra libraries. Did we ever discuss the difference between dense and sparse matrices? I think we did, yes. So I picked dense because this is really the core of any computation. Even sparse computations in the end resort to using dense kernels. And some of these libraries here are really have changed the course of scientific computing. So you cannot really have a class on a scientific computing without discussing these things. So NAG is from the UK. As a matter of fact, it's the oldest library and it's still active. It's a non-profit library. It goes very well beyond linear algebra. It's really a wide collection of routines. So I put it there because historically it's the first one. But I would like to start with ISPEC, which was written in Fortran, of course, like anything else up to Playpack is written in Fortran. So yeah, Fortran is pretty sturdy. Okay, so ISPEC was a library to solve eigenproblems. Eigenproblems, AX equals lambda x, or AX equals lambda bx, standard generalized eigenproblems. The big thing was the introduction of BLAS1. How many of you have ever heard BLAS? Okay, not too many people. So BLAS stands for Basic Linear Algebra Subprograms or Subroutines, whatever. And you see that in the course of the years, 3 levels of BLAS, 3 versions of BLAS appeared. BLAS1 is a collection of functionalities for vector operations. So basically, back then, at the beginning of the 70s already, people realized that there were certain operations so common, they were basically popping up all over in all sorts of computations, so they decided, why don't we just put them together and we write a library, we optimize it as much as possible so that everybody, the whole community, can benefit from this set of functionalities. That was BLAS1, vector operations, and was especially good for vector machines. So LeanPack really changed the landscape because LeanPack now put together a collection of functionalities for pretty much anybody that was doing linear algebra. So now there are linear systems as well as least squares, and ISPEC was also a companion. So now you would have linear systems and eigensystems. Pretty much the whole dense linear algebra territory was covered. And what happens between LeanPack and BLAS2 is the advent of caches, cache memories, and that really changed everything again, because now it's not about optimizing the operations, but it's about optimizing the data movement. I have a slide that explains this. But I don't want to focus too much on performance because after all this is not a class on high performance. Anyway, BLAS2 is a set of routines that combine matrices and vectors. And whenever possible, it's better to use BLAS2 operations rather than BLAS1. Notice that if you have to multiply a matrix times a vector, you can express this operation in terms of vector operations. So if you have to multiply a matrix times a vector, you can take the first row and multiply it, second row multiply. So you can reduce the matrix as a collection of vectors. But you can directly call a BLAS2 routine, and this will be much faster than a BLAS1 routine. Same story for BLAS3, except that BLAS3 really, for the first time, allows you to use your processor at its maximum potential, or something very, very close to that. So if you have matrix operations, BLAS3 can almost exploit the potential of your processor at best. If your processor can perform so many thousands or millions of operations per second, BLAS3 operations almost get there. So as a matter of fact, I always say that that's probably the library that is the most optimized. Then LAPACK, going back to LINPACK, why is it so important? Even nowadays, I don't know how many years later, a bunch of years later, we are more than 30 years later, we are still using LINPACK to rank the fastest supercomputers in the world. What the LINPACK benchmark, it's called, what it is doing today has nothing to do with the original routine anymore. Initially, the story was to how fast can a supercomputer solve a linear system of size 100. Then supercomputers became too fast, so they increased the size to 1,000. And nowadays, the story is opposite. So nowadays, you can solve a problem as large as you want, and as long as you solve it fast. And they measure the speed of whatever size you want. And when we talk about the largest supercomputers, we are in the hundreds of thousands, or actually even millions, in terms of a problem size. Okay, so up to LAPACK, there was virtually no parallelism except for vector computers. But with the ScaleAPACK, now the territory of distributed memory architectures is conquered. So now we have MPI into the mix. PlayPack is the same story, but considerably easier to use and program. And then we have shared multi-core, shared memory, multi-cores. We have a high-level abstraction, something closer to what we see in MATLAB. And then recently, we have, again, multi-cores, special architectures, out of order executions. And there should be another line, maybe when I updated the slides. There should be another line here for, again, the GPUs and elemental, so yet another library for distributed memory. So there is still work going on here. Why? Because every time new type of architecture comes out, new library or new libraries have to catch up to offer the best way of exploiting the processors. So why is BLAS no, I didn't want to show this. Okay, BLAS, where is BLAS? BLAS, here? Yes. Okay. 3 types of BLAS. BLAS 1, as I said, vector operations. So you take a vector x, a vector y, and then you put them together, only that you scale x by a. This is called xp, ax plus y, it's called xp. This is a dot product. You compute the inner product of 2 vectors. So x and y are inputs. Alpha is another scalar as input, and you update it. You update alpha or whatever, you spit out dot. BLAS 2, now we have matrices as well as vectors. So A is a matrix, x and y are vectors. This is nothing else than a matrix vector product. It's called GEM-V. This guy over here, what is it? Yes, of? It's a solution. What did you say? It's this is absolutely not the inverse of a matrix. This is a solution of a linear system. So you have to take this guy and move it on the left, it becomes ay equals x. And within the BLAS, A must be triangular. So you cannot solve a dense linear system. You can only solve very, very simple linear systems, in particular triangular linear systems. Then we move to BLAS 3, and now we work strictly with matrices. And this object here, this here is called GEM, General Matrix Multiplication. And this is the fastest or the most optimized piece of code in scientific computing, for sure. This is used to determine how fast your processor can go. At some point, I don't know whether today I have time or not, but at some point we will discuss on how to measure the speed of your code, of your algorithm. You could simply time your algorithm, but that's not a very good measure. Better way to do it is to see how well your algorithm exploits the potential of your processor. To do this, first of all, you want to see how fast your processor can go. Just imagine you have a car. You don't want to see how fast you get to the target. You want to see how fast you're going compared to what the car has to offer. And okay, you could, in principle, just look at the manual and say, okay, this processor is supposed to perform so many operations per second, same as a car. You just look on the odometer and you say, oh, look at that, it says 260. That doesn't mean that the car makes 260. Same for the processor. They tell you that it can go this fast. It doesn't mean that it can actually perform operations that fast. GEM is used to assess the actual speed of a processor. So it's very, very, very unlikely, not to say impossible, that you will ever write a program that goes faster than GEM. Notice that also that every other BLAS 3 routine other than GEM is written in terms of GEM. Why? Because GEM is so optimized that everything else is built on top, so that if you speed up GEM, everyone else benefits. And also notice that even though BLAS 3, this thing can, in principle, be broken down in terms of BLAS 2 and BLAS 1 operations, this does not happen, and BLAS 3 is solved on the spot. So a BLAS 3 operation is reduced and brought down to small BLAS 3, but then that is computed directly without subcalls to lower level BLASes. Okay, what is this guy over here? It's another BLAS 3 operation. Say it, just say it. Okay. It's not a matrix inverse, it's the solution of a triangular system. The difference is that here I was solving for one right-hand side, one vector. Over here, I'm solving for a collection of right-hand sides. Here there is a mistake. C, oh yes, C, even this is not true, okay. They don't have to be n by n. And the same here, this matrix doesn't have to be n by n. A must be n by n, that is true. Okay, and this is the only performance slide that I will present today, or let's say the only piece of discussion about high performance that I will present today. Why is BLAS 2 better than BLAS 1, and why is BLAS 3 better than BLAS 2? Everything goes down to memory references, so how many pieces of data you have to gather and how many operations you perform on these pieces of data. So, level 1 BLAS, memory references. How many times do we have to access memory to perform a level 1 operation? Let's just take, for instance, the XP. We have to read X, which is n elements. We have to read Y, which is other n elements. We have to read alpha. Alpha is a scalar, so it's only one. So it looks like we have two n accesses to n plus 1 accesses to memory. Why did I write 3? Well, I also have to write why. So it's 2n reads and writes. In the end, it's 3n accesses to memory. How many flops? Flops, floating point arithmetic, floating point operations. How many flops am I performing in an AXP? So alpha times x, I scale all the entries of a vector, so it's n operations, and then I add everything together, 2n operations. So if you put everything together, turns out that as a ratio, you have something less than 1. It means that you're, on average, not performing even one operation per data, per memory access. That's not a very convenient situation. If you want, you can try over here. So this is not true only for AXP. It pretty much holds for all the BLAS1 operations. Okay, let's look at BLAS2. What happens in BLAS2? How many references, memory references do we have? Yes, n square. I like that because now we have to read a memory. We have to read a matrix, which is n square. Then, yes, of course, we also have to read two vectors, and then we have to write a vector. But the order of magnitude is n square to read the matrix. Okay. Now, you guys seem to have problems with this. What about flops? How many flops do we perform? Yeah?
If you put n to the 2.371 or something.
No, that's matrix product. This is just matrix vector. We are here.
A was triangular?
A is full. Here is full.
Okay.
Down here is triangular.
So it's n square also.
Yes, it's n square. As a matter of fact, you could say that it's 2n squares, but you could even see a 3n square, but yeah, it's an n square. Let's say that it's 2n square, so the ratio, at least, it's bigger than 1. It means that if I access the memory so many times, per access on average, I perform 2 operations. At least it's more than 1, okay? Now let's go to BLAS3. Memory references. You were in high performance, you know that. You've seen this. Yes, it is 4n square. So I read A, I read B, I read C, and I write C, so it's 4n square. How many operations did I perform? I mean, am I performing? Sorry? N cube, yes, or precisely 2n cube. So now, all of a sudden, we have an n in the ratio. So it turns out that the larger the matrix is, the better it is, the better the situation. That's why BLAS3 is so important. And that's why you want to use BLAS3 and you want to make your problems as large as possible. You're not going to get very good performance for super small problems, but when your matrices start being in the neighborhood of 100, 150, 200, even better, you get jam to be almost as fast as the theoretical peak. Yeah?
Why is the ratio important, or what does it indicate?
So the ratio is important because the cost of a memory access is much higher than the cost of an operation, significantly higher. The processor basically cannot operate unless the data is sitting in the registers. Every time it has to perform some math, it needs to go to the memory, fetch data, bring it to the register. When data is in the registers, processor is super fast. The problem is that going to memory to fetch and to write, it's much more expensive than doing operation. So having something that performs a lot of operation on each piece of data means that you are amortizing the data movement with a lot of computation.
So it's more like a buffer thing.
It's more like, yeah, it's sort of like that. And I think I don't want to say much more about this today, but I want to show you what BLAS is like. Yes?
Is it really using an n-cube algorithm for matrix multiplication?
Yes, absolutely, yes. It is absolutely true. It's one of my exercises in class to show that in principle we can use a Strassen to speed up the matrix-matrix product to get something that is faster than BLAS. In reality, the numerical stability of Strassen is not enough to guarantee usage in every situation. So for now, the n-cube algorithm is actually used, yes. Okay, and this is the BLAS. As you can see, it's divided in 3 sections, BLAS 1, 2, and 3. Now let's try to load this up. This is the lingo, so this is how the BLAS routines are called. BLAS 1 routines are not super important. The important ones are scale, copy, and AXP, dot, and norm. Yeah, the norm of a vector, of course. So the interface is standardized, is fixed. So it doesn't matter which BLAS library you're using, the interface will always be like this. And BLAS is written, or was written, in Fortran originally. So keep that in mind when you're passing matrices. BLAS assumes that everything is stored by columns. So on these sides there are the names, here are the parameters, and on this other side, if I can go there, yes, there is the description of the operations that are performed. This is swap, scale, copy, AXP, dot, and so on, norm2, and so on. Okay, let's go back, BLAS 2. Now we have matrices into the mix. And together with the matrix, there is this LDA. LDA, it's called the leading dimension. And I have to explain this. Again, those of you who know me know LDA already, but I have to cover it for everybody else. We are now in memory, and we have a matrix. Matrix is a two-dimensional object. Too bad that memory is a one-dimensional object. So since we are in Fortran, the matrix will be stored by columns. What does it mean? It means that this beast is a very, very, very long array. The first part of the array is exactly the first column, and then once we cut, the second part of the array is the second column, and so on. So it's a streamline. You get here, and from here you go back here, and then here, back here, and so on. Okay. The matrix is passed by a reference in Fortran, so in reality we only passed the address in memory of the first entry, and this uniquely identifies the whole matrix, almost uniquely. So let's say that A points here. Then what do we need to identify this matrix? Well, for sure we need to know how many entries each column has. We need to know how many columns we have. So far, so good. There is this extra parameter called LDA. What does it tell me? What does it tell me? Yes. It tells me if I'm here in position ij, and let's say, so this is whatever, I'm accessing entry ij. Now, the next entry down here would be I plus 1j. So we have two successive entries. How far away are they in memory? So if in one memory location I have ij, where is I plus 1j? It's just the next memory location, okay? Okay, so, but now, if I go from ij to, I need to repeat this. This is awful. Let's try again. So, like this, it's between ij to I plus 1j. And the distance is 1. So we go from one memory cell to the next. Now the question is, what is the distance across? So what if I want to access the matrix not by rows, but not by columns, but by rows? So where is that? How many cells, how many memory cells away is this guy from me? It's, in this case, it seems to be n. So because I would have to march the matrix down here, then I have to start up, back, and if you count, it's exactly one column, so the distance would be n. Okay? Now, let's take a much smaller matrix. Let's say that this is 5 by 5. So it looks like the distance, the vertical distance is always 1, and the distance across is the same as the size of the column. That's what we are deducing from here, okay? So let's take this matrix 5 by 5, but let's say that this matrix comes from here. So we are looking at this matrix, which is a portion of a bigger matrix. And this happens all the time. This is super common. So now we are here. What is the distance between I and ij and ij plus 1? That's 1, yes. What is the distance between ij and ij plus 1? It's n. That's the answer. So even if I have a small matrix, the distance across, it's n. And where is this n coming from? It comes from the fact that this matrix here is really embedded in a much larger matrix. And so I don't have to look at the size of this little thing. I have to look at where this small matrix is coming from. So likewise, the answer for the big matrix here, you cannot really say that the distance is n unless I tell you whether this is a matrix that lives by itself or maybe this is part of an even bigger matrix. And if this is part of a bigger matrix, then this is not n, but it's the same as the size, whatever this is, size of the even bigger matrix. So when in order to fully identify a matrix, you have to say how many rows it has, how many columns it has, where it starts from, and LDA, the leading dimension, which tells you the distance between two adjacent entries on a row. Questions?
This distance of 1 to the next column can sometimes be greater than 1.
1 to the next row, you mean?
Yeah.
No, In BLAS, this cannot be. There is a lot of fuss these days to make this more general. There are situations where you would like to have a stride, it's called. And for now, this is not accepted. So.
Does this only, this MBA, does it is it only greater than the size of rows when it's embedded in a larger matrix, or does BLAS do something like padding, like C++ does for structures?
No, there is no padding here. No padding. So it's the leading dimension is strictly just the size of the largest matrix that embeds this object. Wait a second. Similarly, we can talk about vectors. So the same concept for a vector applies to a vector. So if we traverse a vector, what is the distance between one entry and the next? Thank you, Tamo. Yes, what is increment x? So why is it not 1? Why is the distance not always 1?
The vector does not need to be stored in one could be a row of a matrix.
Precisely. So if this vector comes from an horizontal piece of a matrix, now this entry here is this entry here, this entry here is this entry here, and so on. Now they look like one after another, so adjacent in the vector, but really in the memory they are far away. How far away as the yes, as the leading dimension of the matrix. When you work with vectors, it's not called the leading dimension, it's called increment. So increment x would be the increment on the vector x, increment y, and so on. The concept is exactly the same. It's the distance between two adjacent entries in the vector. And so if we go back to level 1 BLAS, we see that every vector has its relative increment, x increment x, y increment y. Now when we go to BLAS 2, now we have matrices, we have matrix and leading dimension. When we go to, let's see, matrix here is identified by mn, leading dimension, and then we have a vector and we have the corresponding increment, another vector, a corresponding increment. It's always like this. In BLAS 3 we have 3 matrices, 2 or 3 matrices, and for each matrix we have leading dimension A, leading dimension B, leading dimension C. Okay? I wanted to say something else. Let's look at you see that there are multiple operations associated to one name, one same function. For instance, GEMV, which is multiplication matrix vector, means general matrix vector multiplication. What does general mean as opposed to triangular matrix vector multiplication or symmetric matrix vector multiplication? So GEMV is associated to a bunch of different versions. In particular, you can do y equals ax plus, well, it's this, alpha and beta are scalars, and x, y are, well, alpha, beta, x, y, and a are all input quantities, and you want to compute x. Basically, you are updating x by scaling it and adding alpha a x. But the same function can also perform this. So even though you pass a matrix A, you can multiply, you can perform the product between A transpose and X. So you don't have to call different kernels whether you want to multiply a matrix or its transpose. BLAS does all of that for you. You just simply have to pass these initial arguments, trans, which might be trans, no trans, or yes, no, and that means whether to multiply the matrix as it is or to transpose it and multiply. Over here we have up low, which means we are working with triangular matrices, and we want to specify whether we are working with a lower triangular or with an upper triangular. So it's up or low. Okay, diagonal means that you can specify what is sitting on the diagonal. All of these are discrete arguments, so they can only take a finite, a very well specified set of options. Oh, and also something else that I should say is that the first character, it's an X. Actually, it's not an X, it's a wild card. You can substitute this with any of S, D, C, Z. S means single precision, D means double precision, complex single, and complex double precision. So most of these routines appear in 4 different flavors, variants, depending on whether you will work in double precision or, well, with real arithmetic or complex arithmetic, you want SD or a CZ, and whether you want single or double precision, it's SD or a CZ. Okay, and then finally, let's go to BLAS 3. Now we have only matrices, and the operations, now these are fun, these are a little bit more involved, but really fun. So op A means that you can have A or transpose A. Op B means that you can have B or transpose B. So that first routine, which is jam, covers all at once A times B plus C, A T B plus C, A B T plus C, and A T plus C. Okay? And in fact, it covers even more than this, because not only can you transpose, you can also conjugate these matrices. See, you can also go for X, H, but I think that's enough. Okay, what other kind of operations do we have? Still matrix products. This is a circ. You multiply matrix times its transpose. This is circ 2K. You do this really interesting operation. So you overwrite C, well, you update C with A times B transpose plus B times A transpose. And then you have a triangular linear systems with multiple right-hand sides. So now B is not just a vector, it's a collection of vectors. And this is it. This is BLAS. And you guys will be using BLAS. We will be using BLAS. Questions about BLAS? I want to point out that all the other libraries that I have shown here, all of these guys here are built on top of BLAS. LAPACK really took LINPACK and rewrote it, so that the routines could take advantage of BLAS3. Scale APEC, of course, uses BLAS3. Playpack, Flame, everything here is built on top of BLAS3. And as well as BLAS2 and 1, because not every operation can be expressed in terms of BLAS3. But whenever possible, you guys want to go for BLAS3. And now I give you an example. So now we talk about Cholesky factorization. Okay, linear algebra. We have a symmetric matrix A. This is input. It's since it's symmetric, of course, is a square. It's more than that. It's a symmetric positive definite. If you know what that means, good. If you don't know, just believe me. It's a symmetric positive definite. It's an assumption. What it means under these assumptions, it means that I can find a matrix L, lower triangular matrix L, such that L times L transpose equals A. Notice that A is the input, and L, it's called the Cholesky or Cholesky factor, Cholesky matrix, gives you a factorization, the Cholesky factorization of the matrix A. It's exactly the same as LU, except that now my matrix has more structure, is a symmetric, and it's a symmetric positive definite. So I want to exploit, I want to take advantage of this structure, and I don't just compute L times U, but I compute L transpose. Okay? So input A, output L. And I write that L equals gamma of A. This is my functional notation, which means I take A, I compute the Cholesky factorization, I spit out L. Okay, let's look at some algorithms for computing Cholesky factorization. How do we do this? We partition everything. What did I do? I decided to split my matrix into quadrants. I didn't say that I'm splitting the matrix right in the middle, in halves. That's not what I'm doing. I'm taking a matrix and I say, let's just cut it so that the top left quadrant is a square, and that by itself already determines that the bottom right quadrant is also squared, and then it determines that whatever is here and here is that this quadrant is the transpose of the other. So this and that, it's one the transpose of the other, and of course both of these things are symmetric. And then there is a nice theorem that tells you that if A is symmetric positive definite, this is also symmetric positive definite, this is also symmetric positive definite, and more stuff like that. So I did not split the matrix in half, I simply partitioned the matrix in 4 quadrants. And now I do some math. I multiply everything out. And then I distribute the equality. Should I put something up here?
It's symmetric, so it doesn't really matter, does it?
Well, this is symmetric, but is this a symmetric?
If it's equal, it better be, right?
I'm not sure. If it's equal, only means that this is not really an equality. This is, I'm setting up an equation. L is not known yet. So the truth is that this object is a symmetric. So it doesn't matter. So the bottom left quadrant will be the same as the top left quadrant. So this equation over here will not be exactly the same as this, but it will be its transpose, so they will be equivalent. So, okay, now I want you guys to do mathematical pattern matching. What do you see in this equation here? Use your pattern matching capabilities. Let's see if you are as good as Mathematica. Tell me what you see, if you see anything.
What do you mean? What do we see?
I want you to do pattern matching. Yeah.
On the top left and the top bottom right,
Mm-hmm.
always have the submatrix multiplied by its transpose,
Mm-hmm.
and here is also the same on the bottom. But because on the top there's only one
Mm-hmm.
side, then it's just one term, and down is two terms. And,
1 second, let me say it loud what your pattern matcher is matching, is seeing. I like this a lot. Is noticing that we are multiplying a matrix times its transpose. We are doing it here, we are doing it here, and we are doing it here. That's what you're saying, right? Okay, I like this. It's a good start. What is this telling you? Yeah.
It's the same problem we are trying to use right now. So it's probably something recursive.
I like this a lot. It's, if I didn't lose the chalk, here it is. It looks like we have a recursive definition. We are trying to compute something such that something times its transpose equals the input. And over here, we are in the exact same scenario. Something times its transpose equals some input. Now the question is A top left symmetric?
You said it is.
I said it is, yes, not because I said it, but because I made sure that it was. I said that it's a square, and so if you take a symmetric matrix and you cut off a square out of the diagonal, that is for sure symmetric. So yes, A top left is a symmetric. Is it symmetric positive definite? Yes, I said it. So that guy over there is a recursive code to Cholesky. So we can rewrite this as L top left equals Cholesky of A top left. That's a really nice start. I like that. Now let me help you a little bit. In this, oh, you don't need help? Tell me.
No, not a doubt, but now we know L top left. And since we can compute that using
Mhm.
the recursive definition, we can use another of the Blas functions to compute the A bottom left.
1 second. Exactly. This is exactly where I want you guys to go. So now, let's say that we know how to perform a recursive call. L top left all of a sudden becomes known. So this is a quantity that now it's input. It was unknown, but now it's computed. So over here, we have it. So it's exactly, I should point this out. Okay. So now I have two known quantities, and maybe I can compute the missing L bottom left. And now he's suggesting that maybe this is another BLAS operation. Which operation? I don't see that far. How many of you have taken performance matrix computations? 3 of you? Yeah, okay. Verena is not here, okay. So what do you see down here? Rotation of the matrix. You mean left or right multiplying. So let's take this. What you're probably trying to say is L top left transpose equals A top left. You're probably saying that this is known, so we can move it around. Yeah, sure. True. So, and how do we move it around? For instance, we write multiply times its inverse. So this guy dies, and what do we have here? This is known, this is known. Pattern matching, pattern matching. No, it's not the same as the top. Yes, but how do I compute this in practice? Which operation is this? Let's look at A bottom left is this part of the matrix. This rectangular guy here. It's not. Wait. L top left, what is that? L top left is from here. It's what comes out of. L top left is a matrix. Because A top left is a square and L top left is the Cholesky factor of the top matrix. So it's a lower triangular, L top left is a lower triangular matrix. Now I have to invert, and I tell you the inverse of a lower triangular matrix stays lower triangular. And then it's transpose, so L top left minus transpose becomes upper triangular. Okay, how many of you think that this is a matrix-matrix multiplication? 1. How many of you think it's not a matrix-matrix multiplication? Let's see if anyone has. Okay, somebody. So there is a conflict. I like this. If it's not a matrix-matrix multiplication, what could it be? Okay, fine. That's probably triangular solve. I like this answer a lot. Notice that we computed L top left. So we have L top left. We don't have L top left inverse or inverse transpose. That's the only thing we have. This is a triangular matrix. It's transposed, that's fine, it's still triangular. And we are trying to compute, so let me show you what the shape is like. This we are trying to compute. Then we have L top left transpose, so an upper triangular matrix, which is known, equals A bottom left, which is also known. So this is nothing more than a triangular solve. In other words, L bottom left is a TR as M. Triangular solve triangular, solve multiple right-hand sides. What are the inputs? Are A bottom left and L top left transpose. Here it is, pattern matching. Let's delete. So we have a recursive call to Cholesky. We have a BLAS tree. And now we repeat the game. At this point, LBL becomes available. Yes?
Now we can just compute LBL times LBLT, subtract that from
Whoa.
right.
Yeah. Wait.
Recursively call.
No, you're running too much. So L top left comes down here. L bottom left comes here. So now it's available. How do we compute LBL times LBL transpose? You are saying that all of these now is available, so we can compute it. Very true. Let's do it. We have to compute it. Pattern matching. So let's go one step at a time. If it's known, let's push it on the other side of the equation. So L bottom right transpose equals A bottom right minus L bottom left transpose. These things are still unknown, but all of those guys now are known.
So LBR is a gamma function of the right side.
Yes, you guys got excited by recursive definitions, so yes, I agree with you. Let me rewrite this. Equals gamma of this. But first of all, we should probably compute this. So how do we compute that? What is it? Let's look at the shape of these things. A bottom right is which part of the matrix? This big guy here. This is A bottom right. Okay. Is it square? Yes, because A top left was a square, so A bottom right is automatically square. Is it symmetric? Yes, because it's along the diagonal. Okay. L bottom left, which part of the matrix L? Here we have our matrix L that we're trying to compute. L bottom left is this object here. So what is that thing? It's a big square matrix minus something like this. It's a matrix times its transpose. I guess you don't have enough BLAS experience yet, but this is called circ. Symmetric rank K update. In case you want to know a little bit more of numerical linear algebra, why is it called the rank K update? Because if this object here, if the matrix consists of n columns, or sorry, k columns, or here k rows, then the rank of this update is k, and so basically this means that you're taking a matrix and you're updating with a rank k matrix. So it's called symmetric rank k update. So we have that L bottom right is Cholesky of circ of, and the parameters are, the arguments are A bottom right, L bottom left. Here we go. And this is my Cholesky factorization. with some dependencies. So first I have to compute the top left quadrant. At that point I can compute the second, the bottom left quadrant, and at that point I can compute the bottom right quadrant. And you see that this is all BLAS except for the recursive calls. Recursive and recursive. Okay, questions so far? How much time do I have left? Not much. Okay, let's look at one algorithm for this. One possible algorithm is we start off, how did I start everything? By splitting, partitioning the matrix in 2 by 2, in 4 parts. So we could, for instance, start off with a partitioning like this, where, in case you don't see it, what does this mean? Okay, this is a 2 by 2 partitioning where A top left is 0 by 0. Yeah, so what would be the size of A bottom left? Zero times n means that it has no rows and a lot of columns.
Okay.
So let's go the other way around. N times 0, yes. What's the size of, well, we know that. What's the size of A bottom right? It's n by n. So we have partitioned our matrix in a way where A bottom right is the full matrix. Okay, this is the beginning. Now I want to set up a loop so that at each step I do something, I make progress towards the end. So let me use this as a first. Then we say while. So we want to continue until my top left quadrant is not as big as the full matrix. While A top left, maybe size top left, not the same as the size of A. Okay, what do I want to do? I want to expose some objects. So my matrix A, which is like this, I want to create something like this. What am I doing? This is A top left, A bottom left, A bottom right. What am I doing? I am exposing pieces, parts of the matrix, so that I can do some computation over here. I can maybe here, I don't know. And then I can move this blue line forward. So down here there will be computation. And then so much better. And then what can I do? Or maybe I can do this other way around. Okay. And now my matrix has grown. So I started with A top left, which was some size. At the very beginning, this will be empty. My A bottom right at the very beginning will be the whole matrix. Then I partition it in 4 pieces. I do some computation, and then I move the pieces onto A top left so that it's growing. What time is it? Oh, I have it there. Let's go super fast. We know that over here I want to do Cholesky. So first of all, I need to assign names. What are these things? A11, A00, A21, A22. So I know that A11 should be Cholesky of A11. Then I know that A21 should be triangular solve. It tells me here should be a triangular solve with A bottom left and whatever I just computed. So triangular solve A21 L1. L11. And then I need to prepare the territory for the next step. So I need to update A22 equal circ A22 L21. Okay, and this is the algorithm. I realized that it was a little bit fast, but I don't have time to show you in MATLAB, so I will do it next time. Just what did we do? We did a recursive call to A11. Then we did our triangular solve down here. And then we performed the circ down here. Once we have done that, we are pushing these objects that we have computed, we're happy with them, we are pushing them on this side of the blue line. And what is sitting down here, we are done with this part. That was the recursive call, so we're happy. Same here, we're done with this, this is happy. Down here, this object here comes, this object here comes from A22 now, because I've pushed these things, I've pushed on the other side. So now I have to do Cholesky of this guy, then a triangular solve, and update again. So I can just repeat this until A top left has grown to be as big as the full matrix. Yes?
Can I do it recursively?
You can do it recursively as well, yes. But for performance reasons, we will not do things recursively. The only recursive calls for us will be when I do Cholesky of this object here in the middle. So, yes, it was a bit fast, but we will do it in MATLAB next time. Yes?
Could we go ahead and always split off a 1-by-1 matrix in the top left and just keep doing that?
Absolutely, that's exactly what we're doing. I didn't specify how large A11 is. If it's 1-by-1, it's called the unblocked algorithm. If it's not 1-by-1, it's called the blocked algorithm. And that's exactly what we're doing. We keep splitting out 1-by-1 entry. We do something, and then we say, okay, we're done with this part of the computation. We will not need it anymore, so we push it into A top left.
Because that would kind of make the triangular solve easy. If you have a triangular matrix of size 1-by-1.
That's precisely what we want. Yeah. You guys have other questions? Then good luck for the competition on Thursday.